ideal gas versus real gas. Now, class, the ideal gas have so many formulas and equations, especially in chemistry, physical chemistry, okay, in thermodynamics, or even physics, okay? But in real gas, it only to uh, the van der Waals equations, okay? Like that. So it's very important to know how compressible gas really is because this is our identification. Okay. The most basic concept for this is the small letter Z. What does it mean? Small letter Z, guys, is simply the compressibility factor. Okay. So we need to derive, okay. I don't think so for this if uh, I really learned this in college. Okay. Because what I did in college, I'll just memorize, okay, a lot of, effort in memorization, but I'll never go into the detail. Now, I'm already a chemical engineer, okay, because I have so much free time now on my work. I really dig it out. Oh, it's gonna be like this. Maybe I know that before, I'll just forgot, but I'll just now discover that it's gonna be the difference or so if I know this before, maybe I could have a very, very high grades in thermodynamics and physical chemistry. Since I don't know this before, okay, then my grades are not that high. Shall we say average or above average, but not very high. Okay, or sakto lang yun siya. Okay? So Z, so we need to derive the Z, the compressibility factor of a gas, okay? Small letter Z. Okay. Now I have one question for you. Is gas is compressible or incompressible? Okay, that's the first question to determine because we are focusing on the compressibility factor from itself word alone. Okay, from the word alone, so that's compressibility factor. It's not incompressibility factor, right? So we need to say gas is somewhat compressible, okay, compared to liquid. Okay, so usually incompressible liquid, compressible gas. Okay, and most ideal gas are compressible. Okay, like that. It doesn't have high compressibility, but it's just compressible. Okay, so like that. Okay. Okay, Z compressibility factor. I put here. Okay, compressibility factor. Okay, here. So this is the first definition to take note. Z is equal to compressibility factor. Okay, now if the gas behave ideally or an ideal gas, so the Z is nearly equal to 1. So it could be 0.98, 0.97, 0.96, but it could not be less than too much than 1, nearly equal to 1, or just equal approximately to 1. Okay, this is an ideal gas. Okay, this one. Okay. Now, if you have to prove this, if you have problem solving regarding the Dalton's law of partial pressure, Avogadro's law of gases, Pascal's law of gases, something like that, the combined gas law, okay, PV in RT, the most gas-gas formula in chemical engineering, okay, and we have also the Gay-Lussac law, Charles law, Boyle's law, okay, something like that. So that is applicable for compressibility factor is nearly equal to 1 or equal to 1. Now, how can we say that it is a real gas or non-ideal gas? So our compressibility factor will be less than 1. Okay. Z less than 1. What is the symbol for less than in mathematics? It's going to be like this. The pointing sharp edge will be away from the Z like this, and it eating up the number that is less than. Okay, so Z less than 1. You know how to put the symbol of greater than, less than. It's very important. Okay. Z is less than 1. So this is real gas or non-ideal gas. Okay? This one. If Z is less than 1, okay, this is a real gas or non-ideal gas. Okay. Now, if the Z also is greater than 1, this is also a real gas. Real gas and non-ideal gas. Okay, like this. So imagine, okay, so if greater than the Z compressibility factor is greater than 1, it's still real gas and an ideal gas. If it's also less than 1, it's still real gas and an ideal gas. So practically, today, nowadays, at this moment in time, August 5, 2021, the gases around me is not ideal. Okay, in real sense of the world, or practically, or in actual scenario, okay, it's not ideal. It's real gas and an ideal gas. Okay, so ideal gas from the word perfect gas. That's why ideal in Webster dictionary, right? Ideal meaning subject to perfection. It's very difficult to attain a compressibility factor which is equals to 1 or nearly equal to 1. So in our chemical engineering or any thermodynamics subjects, we focus more on the ideal gas, right? And then we take for granted the behavior of the non-ideal gas. Okay, in which practically real gas or non-ideal gas exist in our atmosphere compared to the ideal gas, in which we are kept on repeating that in our studies in engineering, especially when we deal with gases in physical chemistry or thermodynamics. So it seems also that it looks like, okay, bookish, bookish, and shall we say, not really that practical. Okay, so I think most probably they are teaching us to extract the basic concept, basic principles, and basic theories only, right? Something like that, or more technical or theoretical, something like that. Because in the real sense of the world, we are surrounded with real gases and non-ideal gases. Okay, now let's explain to this. How can I compute the compressibility factor? Okay, Z. So according to our scientists before and based on my research also, okay, so the compressibility factor is equal to the actual volume of a gas, okay, over the ideal volume of a gas, okay, like that, okay, ganun siya. Ideal, actual or ideal, this one, okay. So we know that. So Z, that's basically a factor. So actual volume of a gas divided by the ideal volume of a gas or the theoretical. Okay, theoretical is not actual, right? Okay, so we will put this one. Okay, My problem now is I have no ink in my paper. Charot! Charot na guys. I have to choose another pencil pen and brush. Hello. Okay, guys. Okay. Now, let's treat that volume actual is just equal to molar volume. You remember that one? I teach you before, molar volume. Molar volume is equal to the volume over the number of moles. And we represent molar volume as Vm. Okay, so our numerator here is Vm, and our denominator here is the ideal volume. And we can equate automatically our molar volume is equal to the actual volume. Okay, that's why I put V subscript small letter m represents actual volume. So our compressibility factor is equal to the actual volume Vm over the volume ideal, which is V capital V subscript small letter I. Okay, now we need to substitute values because we memorized this even before that the formula of compressibility factor Z is equals to the pressure times the molar volume over the universal gas constant times the capital T in Kelvin, right? Gas. Not really that gas, but the PV&RD is the gas, right? What I mean of gas, usually used, very common, okay? Even though we as chemical engineer student or chemical engineering graduates, even though we die, we can still remember the formula of that PV&RT. Okay, until our last breath, we can still remember that formula because it is used most of the times in our curriculum in BS Chemical Engineering. That's what I mean of gas. Okay? Most common and most widely used. Okay? So, our ideal V, I will take first the formula of Z, and we need to prove this compressibility factor because it's very important to determine how compressible the gas really is, how ideal the gas really is, and real gas really is, so that we can solve properly if presented in different future examinations. Okay, you can really distinguish what formulas to be used, right? Not. So Z, okay, Z is equal, oh my gosh, wait, nawala na yun. Sorry, Z, nawa ang ink. It's lost. Lost in your eyes. Sorry, I have to find another. It is one. This will be the last. The last hurrah. Okay. So, compressibility factor is equals. Guys, compressibility factor also, compressibility property is very important in studying of refrigeration system. The cooling process, the heating process, okay, the principle of our RAF, the fridge, it has the principle of refrigeration system. Okay, it's very important there, okay, because it will undergo compression. Okay, so it will be applied there, the concept of compressibility. Okay, like that. Okay, because our refrigerator has refrigerant, that's why it's called refrigerator. You know, refrigerant is a formula that involves carbon, hydrogen, and oxygen. Okay, like this. So Z. Okay, am I correct? Refrigerant, and also the AC has also refrigerant, right? Correct me if I'm wrong. Okay, Z. Z is equals to pressure, molar volume, times universal gas constant times T. Okay. Yeah. Uy, look at this. Z is equals to P times smaller volume times RT. We need to derive this. Why this come out? Okay. So this come out by the concept of Z is equals to the actual volume over the ideal volume of a gas. Okay, now we need to substitute values now. Okay? But the main problem is like that. Okay, how can I do this? Gosh. Oh, like this. Oh my gosh. Okay. So VI. So we have the PV in RT in ideal gas law equation, okay, or general gas equation or ideal gas equation. It's just the same. Okay. So ideal gas PV and RT. PV and RT. It's one, right? PV and RT. So for the value of V, okay, and treat that as VI. I represents for ideal. So VI is equals to the pressure over nRT, right? Substitute the value of VI. Substitute the value of VI in the equation. Z is equals to Vm over RT, PVM RT or Vm over VI. Sorry, Vm over VI. We have now the VI from ideal gas equation. We substituted there in the compressibility factor. Then later we can obtain Z is equals to pressure times smaller volume or actual volume over RT. So let's substitute the VI. Okay, let's have this our equation 1. Okay, equation 1, equation 2. We have to organize so that we can remember. That's the purpose only of having equation 1, equation 2, equation 3. So that somewhere along the way, we can recall that and get that equation. We need to number. Okay, so we go to the equation 1. Okay, so Z is equals to Vm. Okay, Vm over Vi, which is P and RT, right? Over in RT. So bingo, our Z will become PVMRT. Okay, that's why we have Z is equals to PVMRT, which is our equation number 2. So we derive already, right? In a quick manner. Okay. So that's why we have that formula Z is equals to P times smaller volume over RT. Okay, now in the problem, for example, the problem will say, what is the compressibility factor when a gas passes through the orifice emitter or passes through the conduit or passes through the diffuser, something like that. Okay, you know that one? Passes to the diffuser or nozzle, okay, having a pressure of like this chuba chuchu and having a mass of like this, okay, at 10 degrees Celsius. So you can compute easily. We're having this formula. Z is equal to PVMRT. Now you will be confused a little bit because there's smaller volume. So Sotero, how can I find the molar volume? We are only given the mass. Okay, so take note the relationship of molar mass into volume, right? And then you can obtain the moles, and then something like that. You can play around those formulas, okay, and then you can later on you can obtain the Vm, okay, something like that. And then you will also, since I gave you the temperature, right? And you know the mass is there. Okay, so how about obtaining the density at 10 degrees Celsius of that particular gas? Density is equal to mass over volume. So you treat that as a molar density is equals to the molar mass over the molar volume because you are using all molars man siya. as what I told you a while ago, a long time ago. If you use molar in your equation, treat those quantities all as molar. Since Vm, molar volume, is what you want to find, then you have no other choices to get the molar volume because it's given in the problem the molar mass. Okay? So if there's a molar mass, then there's a density, molar density at 10 degrees Celsius. Okay? But take note, if you get the molar density, it's still density there in the handbook, convert also that to molar density. How can you do that? You can do that if there's a chemical reaction involved for that particular gas. Because in here, I'm talking of a gas that is general. I don't specify the gas. If the problem specify the gases reaction, chemical reaction, you can determine the number of moles. And since that, you get the molar density, the density alone is not yet molar because molar density and density is not the same. Okay, so you will just get the density at 10 degrees Celsius, and after that, you will be able to get the molar density. How can you attain that? Because from the word molar, there's involvement of the moles. So the only way to achieve the molar density is through the chemical reactions because it has a number of moles, balanced chemical equation. Okay, so through that, determine the gas, okay, get the density, okay, and play around, you can get the molar density. Okay? And then take note, you cannot substitute directly the density, you get from the table, from the books, or from handbook. You still convert that to molar density because you are finding the molar volume and shagor. Okay, so molar density is equals to molar volume. Oh, sorry, density molar mass over the molar volume. And this is the problem is given a mass, and this is the actual mass we refer to our actual volume. So it's just the same, right? So put that there in the equation and you can get the value of molar volume. Okay, like that. Or you can also use the other formula without involving the density. Okay, you can still find it also through using the molecular weight. Okay, molecular weight. Remember, if you have the molecular weight, you can cancel the chuba chuchu. Okay, and then moles will be left, ganun siya. Okay, so still the same until you can get the molar volume. Okay, so you can get now the compressibility factor if the compressibility factor is being asked in the problem solving in the examination. Okay, like but normally they will mention the type of gas that will enter in that particular pipeline, tank, venturimeter, orifice meter, diffuser, nozzle, hose, or any, any passage for that ideal gas to pass, something like that in the inlet going to the outlet. Okay, normally they will mention the type of gas, so don't worry for the molecular weight. Okay, since there is a temperature, then you can troubleshoot for the density. Okay, density, mass over volume, and treat all as molar. Since in compressibility factor, it is not the volume alone, but it is the molar volume. Okay, you got my point. Ganon. So, bingo, you can solve for the compressibility factor at 10 degrees Celsius of that particular gas. Okay, I'm just having my wild imagination. As I told you before, if you want to become an engineer, you must have a wild imagination. Okay, something like that. Okay, so now, okay, going back to the relationship now because we have this formula now. Okay, now, if I can obtain an ideal gas, which is the compressibility factor is nearly 1 or equal to 1, now I can use a lot of formulas in ideal gas. Okay, I don't have to write that, just put it in your brain cells. Okay, at least there are 12 or 13 equations. First, Gay-Lussac's law. In Gay-Lussac's law, what is that constant? Gay-Lussac's law. What is constant? Hala. Okay, nakalimutan ano. Gay-Lussac's law. Okay, the formula of Gay, if you forgot the constant and you know the formula, then you can get the constant. Okay, and if you remember the constant, then you can get also the formula because it's always pressure, temperature, and volume, three quantities only. Put that in your brain cells. Okay, always three quantities play around in an ideal gas: pressure, volume, and temperature, except for the Dalton's law of partial pressure and the Avogadro law. Okay, and also the Henry law and the Rayleigh law. Okay, lo chuba chucho. Okay, okay, ganon siya. Okay, so you will use Gay-Lussac's law. Since I know that the Gay-Lussac's law is P1 over T1. Okay, P2 over T2. So automatically, the constant is volume. Volume is the constant in the Gay-Lussac's. Okay, in the Charles law, since I know the formula V1 over T1, okay, V2 is equal to V2 over T2, then I know that my constant really is the pressure. Okay? Now, for the Boyle's law, what is the constant? Since I know the formula, P1 times V1 is equal to P2 times V2, then my constant will be the temperature. Okay? Like that. So it's easy to troubleshoot. And this is only applicable for the compressibility factor equal to 1 or nearly equal to 1 because this is an ideal gas equation. Okay? Malong, if it is less than Z, is less than 1 on Z or more than 1 on Z, you cannot apply this. Okay? Upon solving this, Z is equal to P times Vn and RT. And, when I was in college, I was not aware for this. Okay? I was not aware based on my reading, research, and ito pala siya. So if I know this before, it's really for me to troubleshoot what formulas really to use. Okay? Directly, not too much thinking, like this. Okay? Okay. Anyhow, it's still okay. Okay, now going back to the ideal gas law. What else? For the shot, Gay-Lussac's law, Charles' law, okay, the Boyle's law. Okay, now, Avogadro law. Avogadro law, Mr. Avogadro discovered the constant 6.02 times 10 exponential to the 23. So the unit of this Avogadro law will depend on the substance being considered in a chemical reaction. It could be an ion, it could be a mole, it could be a molecule, like this, or it could be a formula unit. Okay, so you can play around the conversion factor, then you can obtain if it is an ion, an atom, a molar, or a mole, a molecule, or simply a charge, okay, or formula unit. Okay, so you can feel the problem, okay, if it involves Avogadro law, Avogadro constant. So he discovered this one. Okay, now he specialized also another study regarding ideal gas law. So it's all about the proportionality of the volume of a gas and the amount of the gas. As I told you before over and over again, when you speak about amount, that is a mole. A mole is a unit of the amount of a substance in a chemical reaction. So in here, we are focusing on the gaseous state. So our moles here is in terms of a gas. Okay? Like that. So our formula will be, since directly proportional, the number of moles or the amount of gas to the volume of the gas. So we can say volume 1 over small n1 is equals to volume 2 over small n2. I don't have to write just put on your brain cells. Okay, because it will take time for me, then my ink will be consumed. Okay, I assume that my audience are sciences courses, be it chemistry, be it chemical engineering, be it pharmacy, forensic science, medical technology, all about sciences courses, chuba chuchu. Okay, but if your course doesn't involve sciences, for example, business administration, psychology, College of Arts and Sciences, okay, and then political science, okay, bachelor's in accountancy, something like that, then you have to research in the books, okay, because this is not your really your line of specialization, okay. Because I don't write, okay, like this, okay, because you know the ink will be collapsed, okay. Just get a blank sheet of paper or retain in your brain cells, okay, something like that. Okay, that is Avogadro law. V1 over N1 is equal to V2 over N2. N stands for the number of moles of a gas. Okay, ganun siya. Now, ano na siya? 4. So number 5 equations. We are referring to ideal gas law because I said before, Z is equals to 1 man good siya. Okay, if we encounter problems in the future like this, especially in the board examination or any whatever science examination that you are facing to in the future, something like that. Okay, so that's number 4. Number 5, the Dalton's law of partial pressure. Okay, favorite kinina ko siya. Okay, total pressure, charot. Total pressure is equal to the partial pressure of each individual component of a gas. So PT is equals to PA plus PB plus PC plus PD. This A, B, C, and D is individual component and stated partial pressure, individual component of a gas. Okay, I'm saying partial pressure. Okay, very important the term partial because we have also total pressure. Okay, and we have also the absolute pressure, atmospheric pressure, vacuum pressure. Okay, so you should apply that here also. Okay, the absolute pressure. Oh, come on. Absolute pressure is equals to the atmospheric pressure plus the gauge pressure. Atmospheric pressure is equals to the gauge pressure plus the vacuum pressure. So these kinds of pressures are not applicable in this Dalton's law because we are dealing with partial pressure. Okay? So normally, our total pressure will be the atmospheric pressure or the total pressure, okay, in the environment considered, something like that, okay, PT, okay, or total pressure. Usually the atmospheric pressure talaga siya because all those gases exist in the atmosphere, okay, something, ideally, we're not talking here of real gases, right? Ideally, okay, something like that. So we have 5 na, 5 equation na no. So PT, PE, PB, PC. So aside from that, we need also to compute the mole fraction. Okay, because in this law of Dalton's partial pressure, the number of moles are very important. Okay, so Na, like it like that. Okay, Na is equals to mole A over mole total. Okay, mole total meaning the total number of moles of those gases combined. Okay, and then the numerator will be the number of moles of that one particular gas you are referring to. Oh, the same also with B, gas B, gas C, gas D, o ganon siya. So that is mole fraction. Not only that, you can also have the volume fraction. Okay, same story. The volume of the component A gas over the total volume of those partial volumes. Because we are now referring to volumes. So partial volumes. Okay, because we are using partial man talaga. Partial pressure, partial pressures. Volumes, so partial volumes. Ganon. Okay, or we can use also the mole fraction, volume fraction, and pressure fraction. Not too much with the mass fraction, ha? Okay, it's gonna be 4 all the time, eh? Okay, mass fraction, mole fraction, volume fraction, and pressure fraction. Okay, now the mass fraction is not so applicable here. This is more applicable in the thermodynamics, which is the dryness fraction of the mass of the vapor, the saturated vapor, the saturated liquid, right? That if you remember, the saturated steam table, the saturated inorganic liquid table, that's more applicable there, somewhere out there, okay? But if the problem also requires, then we do it, okay? Maybe the problem will start with a mass. not a volume. Then you have to convert the mass to volume, right? Okay, because it's gonna be like that, or you then convert to pressure. Okay, as long there are quantities on this 5 already. What else? Okay, what else? The Pascal pressure is just equal to the one I mentioned later. Now, absolute pressure is equals to the atmospheric pressure. Ganon, di ba? Atmospheric pressure for the gauge pressure. The gauge pressure, guys, is the gauge pressure attached on the equipment. Okay, if you are working in a plant, then there's a gauge pressure on each equipment, right? In the tank, vessel, process vessels, or any type of equipment. There's a pressure, of course. If there's a liquid inside the tank, there's a pressure, right? Of course. And then if it's a gas, if it's a liquid like this. So they attach the pressure gauge, that is your value of your pressure gauge, plus the atmospheric pressure in the environment you consider the wet. Okay, that is the absolute pressure. Okay, like that, because it's rare only in the sea level. Because the vacuum pressure, mga good guys, is below sea level, and it's also unusual for that, right? So it's not all the time practice to do that. Okay, so unless it's specified on the problem. Okay, like that. So 6 na siya, including the Dalton's law. Number 7 is the gas-gas formula, PVNRT. That's what I use here. This is the ideal gas law equation, most used of the time. Okay, 7 na siya. Number 8. Number 8. Remember, the kinetic molecular theory also follows ideal gas behavior, right? So, average kinetic energy, pangwalo na, is equal to the 3 halves times RT. R, capital R, universal gas constant, and T, temperature in Kelvin. Kelvin is equal to degrees Celsius plus 273.15. R is the universal gas constant. I only memorized 2, okay, in terms of liter atmosphere and in terms of joules. In terms of liter atmosphere, it's gonna be 0.08205 liter atmosphere over mole Kelvin. And if you try to consider joules, it is 8.3145 joules per mole Kelvin. And the rest will be derived from the ideal gas law PV in RT, assuming an ideal gas of 1 mole at a standard temperature, okay? At a standard temperature, I mean 0, right? It will never 0 in the equation because you still add to 73.15 because that T here, T there is Kelvin. Malong? Okay, capital T there is Kelvin. Though our standard here is 0 at STP, it will never be 0 in the equation, right? Okay, now your R, I mentioned it already, and then the pressure dependent, then you can get any types of R you want, okay, through conversion factors. Even though you will not memorize, you can derive your R if you know this ideal gas at STP. STP meaning standard temperature at 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere. But remember, it's not always 1 atmosphere. It is 1.013 bar, 760 torr, 760 mmHg, 101.325 kilopascal, 101,325 pascal, and 14.7 pound per square inch. So there are at least 7 units of atmospheric pressure, and from now on, memorize it, put that in your brain cells. Okay, especially if you want to take BS chemistry or base chemical engineering. Okay, or any engineering courses, especially because this is studied in thermodynamics, fluid flow, okay, fluid mechanics, okay, fluid static, like that, okay, fluid kinematics. Wow. What is the difference between kinematic and kinetics? I don't need to discuss that one. Later, it is not our topic, okay? We need to identify. Ganun talaga siya. If you are an engineer, you need to detail the definition, what is that all about, so that it's easy for you to understand, to incorporate each formula out of it, because there are formulas that derive from the terminologies out of it, something like that. So it's easy for you to troubleshoot the exact formula if you forgot. Okay, something like that. Okay, 7 na siya, o 8 na siya, no? Because of KMT. KMT means kinetic molecular theory of ideal gas. Okay, now for the velocity aspect, wow. Because normally, a gas will pass through a pipeline, a vessel, a orifice meter, a venturimeter, a nozzle, a diffuser, what else? An elbow pipe, okay, or anything chuba chuchu. Okay, it's mentioned in the any kind of problems, right? We need to consider the velocity, of course. Okay, and the velocity is dependent to the diameter of the pipe, the inlet and the outlet, and also determined by the molecular weight. How heavy is that? How light is that? How fast and how slow is that? Okay, so that is velocity all about. Okay, density, how heavier, how lighter, like this. Okay, so in here also you will connect the mass flow rate and the volumetric flow rate. And then again, you will do the overall material balance, okay, involving the energy balances also, if you like, if it is applicable. And then you insert and incorporate still the ideal gas law equations that I mentioned above, the A. It will be rumbled now, okay, because there's a movement and flow magud siya. Okay, the velocity, and then sometimes we consider the viscosity also, if there is a resistance to flow, okay, of that particular gas. But anyhow, viscosity will be applicable only more on the liquids, incompressible liquids, not so much with gases. Okay, because gases are non-Newtonian fluid man siya. Wow. So meaning to say, di na kayo siya mo kuan ba mo ma-apply. Charot. Okay? So basically, Newtonian fluid ang mga liquid. Okay, non-Newtonian fluid ang mga gases. Okay, you can see that in the graph. If you graph that one, you can really understand the behavior of those phases of matter. This is phases of matter. Okay, liquid, gas. Solid is a little bit far behind because solid is very definite. We can visualize that in our naked eye. Okay, that's the only difference. And the solid is very visual. We can see that immediately. We can compute directly because it can be seen. Okay, but gas we can never see the vapor. Okay, sometimes you can only feel something like that. We can smell. Okay, that's the difference. And solid are not being considered too much in the higher subjects. Okay, but in the lower subjects, it's been considered, especially in the strength of the materials, engineering mechanics, bridges, roads, the solids. We can see that in our eyes. Okay, it's good to study if you can see in your eyes. Okay, definitely because you can understand normally. Okay, if you study those things that you can see, then it's very easy to understand. You can feel it, you can hold it, you can touch it. But if you study a particle, an molecule, you'll never see that, and you can only see that through a microscope. That would be a complex scenario already. Okay, and we chemical engineers study that. Okay, more on imaginary. Okay, like that. So molecular talaga siya, no? Okay, dapat yung brain cells namin molecular talaga siya. Charot. Okay. So that's why a lot of engineering students in first year, a lot will take chemical engineering and then they will shift into another courses in engineering because they feel something, oh my gosh, what's this all about? It requires a lot of memorization, okay, chuba chucho, okay, like this. I remember before when we are first year chemical engineering, we are 50 or 60, and then second year, we are 30, and then third year, and then we graduated only 20 plus. 20, yeah, 20 plus, yes. 20, almost 20 out of 6, okay? Because they feel something different. My gosh. Okay? Because nobody wants to complicate ourselves, right? We want our lives to be easier. normally, right? In the real sense of the world, to be practical, we want ourselves to be easy, to take it easy, and that's we don't want to be burdened, to be complicated. That's why others choose to be in that way. Okay, but there are also other people loves challenges like that, and they proceed farther, something like that. Okay, or they love really sciences. Okay, so going back na tayo, walo na siya, no? Okay, number 9. For the velocity aspect, oh my gosh, okay, we need to consider the root mean square velocity of an ideal gas is equal to the square root. Oh my gosh, may square root na siya. Charot. Square root of 3RT over the molecular weight. The molecular weight is capital M, ha? Or the molar mass. More na siya. Okay? Molar mass, guys, will be equal to molecular weight if we are referring to chemicals or a compound. But then if you are not referring like that, it will be not the same. You will not use molar. For example, laptop, the mass of the mouse, the mass of the laptop, the mass of the ball pen, the mass of the notebook. Uh, you will never say molar mass. You will never say molecular mass, molecular weight. You will just say mass. Okay? Something like that. Because it's possible also in the problem. Calculate the density of the laptop. Ganon. Okay? In the particular situation. And then you will go, oh my gosh, sanay tayo sa mga liquid, sa mga gas. How can I do this? Okay? Apply din to ni mga buoyancy. Okay? Theory of Archimedes principle. Okay? Dropping the, if you try to put that in a liquid, and there's a density of a liquid, and then subtract it, and that will be your mass of the laptop. And ganon. Okay? Assume that the laptop is defective already. Because if it is a new laptop or a good laptop, why you should dip in the water? This is gonna be like this, right? This is very wild imagination. Okay, if you really want to become an engineer, this is possible also. Sotero has a 2-kilogram defective laptop. He dropped on the basin of water. Okay, calculate, calculate the force and the density of the laptop upon dropping in the basin. Oh, ganon. So, get the mass of the laptop, and your reference will be the density of water, because this is a basin of water, right? So, the formula of the density, which is that, okay? And then you will get the density of the laptop through that, because your basis will be the density of water at standard conditions. Okay? Because you drop from there. Or else your problem has a given of the density, so that you will never get the density anymore. Because guys, density applicable also to solid, but rare cases lang yun talaga siya. Okay, rare cases. Okay? So for example, density of an ice. Ice is a solid, right? Okay, so density of a dry ice. What is a dry ice? Fury. Okay, dry ice, guys, is a solid carbon dioxide. Okay, and then what is a laughing gas? A laughing gas is a dinitrogen oxide. Okay, you should know also the trade name like that, because it will be coming also in the board examination or in the future examinations. You have to identify what is a muriatic acid. A, sulfuric acid, nitric acid. Okay, muriatic acid is just the same as hydrochloric acid, trade name only. Now, what is aquaxinada? Okay, so that is only hydrogen peroxide H2O2. Sometimes you also familiarize the chemical trade name. Sometimes also in the question, they will give the chemical trade name, and you will identify what specific chemical formula is that. Okay, so that usually comes out in the physical and chemical principles coverage. Okay, it's gonna be like that. Okay, especially for that. Okay, going back, nilayo na pa. Okay, number 9. Number 10. Oh, number 10. What else? What else formula of ideal gases? Okay. What else? Okay, daghan naman kayo siyang formula. Okay, ang ideal gases. What else? So 10. Let's stop for 10 for a while, because I forgot the other 2, other 3, other 4. But if we will derive that, we can also obtain. And now we go to the non-ideal gas or the real gas. So if the compressibility factor is less than 1 or greater 1, so we will use the van der Waals equation. Okay, so van der Waals equation, what is our formula? I teach you already last weeks, previous weeks. Van der Waals equation is equal to the pressure is equal to the number of moles times the capital R, the universal gas constant, times the big T, Kelvin, over the big V, which is the volume regular. Volume regular meaning it's not a specific volume, it's not a molar volume like that. That's what I mean by regular. Okay? Ako dyan siyang specify. Okay? So, V without any subscript is the regular volume. Okay? Ganun siya, chuba. Minus, denominator niya siya ha, minus the number of moles times the B. What is the B? B is the constant that describes the strength of the gas particles. Wow. So if it is the strength of the gas particles, meaning the behavior, how it behaves when you put that in a certain container, something like that. The strength, magud siya. Okay, strength. Oh. Okay, ako na lang isuwat eh. Taas man yung van der Waals. Charot. Okay. Actually, I love this too much. This van der Waals equation. Pressure is equals to nRT is equals to V NB minus A, okay, and V squared. Okay. Van der Waals equation for non-ideal gas and real gas, Z is less than 1 and Z is greater than 1. It's 1. Okay. Okay, what is an A? A and B are constant. A is a constant that describes the size of the particle. Size. Okay, like this. So in this equation, guys, we can obtain this also from the PV/RT. Okay, we derive this from the PV/RT. So kusgan gid kaayo ang PV/RT because he is the source from the van der Waals equation. Okay, gahit siya. Okay, powerful because the van der Waals is coming from the ideal gas. Okay, so it's coming from the like this. P pressure like that. Let's chuchu. Okay, pressure plus the pressure fraction. Okay, times the volume plus the volume fraction. Okay, like that, and then is equals to nRT. That's why it's gonna be like that. Okay, you get the point? So pressure plus the pressure fraction, okay, like that, and then times V. This one, guys, P close and open parenthesis plus pressure fraction PF subscript small letter F times volume plus the volume fraction. Okay, is equals to nRT. Okay, guys, okay, now our P is gonna be like this. Okay, you can add the fractions. Okay, so this V is more on the V minus NB. Okay, like that, and this P is more on the nRT thing. Okay, that's why it arrived. If you substitute that one, you can really obtain what you are being added. Okay, because we have already the final formula of van der Waals equation in terms of P, right? And then if you substitute the P in this here, then you can get what is being added, the fractions. Could it be the volume fractions and the pressure fractions? I don't have to do that because I still have to derive again. Okay? Nakakaloka. And it will take time again. Okay? I have still 20 minutes more. I have another appointment. Charot! Okay? Ganon. So in terms, guys, by the way, guys, the pressure fraction is more on the intermolecular forces of attraction consideration. Okay, intermolecular forces of attraction consideration. And then the volume fraction is more on the number of moles or the volume measured. Because the real gas is an ideal gas, it is occupying in a measurable volume. Okay, measurable volume, meaning it will measure the volume. And then it will consider also the intermolecular forces of the molecules. Whereas the ideal gas, it never account that one, the intermolecular forces of the molecules. Okay, like that. And then it will never also account the measurable volume because it assumes in ideal gas that it is a dimensionless points. Okay, or immeasurable. That's why. Okay, like that. So that's the applicability, something like that. And then the ideal gas also in terms of pressure and temperature. The ideal gas, as you can observe, if you solve so many problems, the temperature are always high. Okay? The temperature are always high. Why? The temperature is always high because you need to have more kinetic energy. Okay, the more kinetic energy, the more it will, the molecules will collide with each other or bond with each other. Okay, so that it will escape. So if the molecules will escape in the container, no need to measure the volume because it will just escape in the atmosphere. Diba? But in the van der Waals, it's not like that. You have to consider the volume. Because the temperature also is low. There's no high kinetic energy there. Okay, it's not being heated that much. So, again, ideal gas, low, higher temperature. So, automatically, the pressure will be low. Okay? And then in the real gas, temperature is very less because you don't have to heat that one. You don't have too much kinetic energy to do that. Okay, like that. So it is having a higher pressure. Now, if you see the problem also, aside from the compressibility factor chuba chuchu, you will also try to consider the relationship between the temperature and the pressure. How can you apply if it is an ideal gas or a non-ideal gas or a real gas? So at that time, you can easily solve the problem. And you can troubleshoot the appropriateness of your formulas and equations now. Okay? Actually, that would be the first, but I don't have this in college. This, concept. Okay? Like that. Due to my research only. Charot. Okay? Something like that. Okay, you know na. And then you have also the other version of Van der Waals. What is the other versions of the Van der Waals Sotero? Charot, yan talaga. Okay. What's the other version? Okay. The other version will be like this. Pressure is equals to RT, okay, Vm minus B, okay, like that. And then minus A over Vm raised to the power 2. Okay, this is the other version of the Van der Waals equation. Now, you can also classify this one because we have now the Vm. This is molar volume, right? Now, if the problem will not state the molar volume, then use this one, the original equation of the Van der Waals. Okay, but if there is a molar volume chuba chuchu in a chemical reaction, use this number 2, something like that only. You have to analyze. Okay, as long as you know that it obeys the lower temperature, high pressure, and compressibility factor Z less than 1 and higher than 1. Okay? So that would be real gases. Okay? Something like that. So in Van der Waals equation, there are 2. Okay? Guys, if the constants A and B are not given in the problem, you will force to find it in the handbook, Peary's Chemical Engineer's Handbook, or in a chemistry handbook, yung Fred Moore, orange color. I have that in my room. Okay? Fred Moore chemistry book, the orange one, like that. And it's there in the table, in the back portion. But in the Peary's Chemical Engineer's Handbook, more on the unahan siya. Parang gano'n siya tubod chuchu. Okay? Like this. But sometimes also the problem will give the A and B. That would be good because that will be your identification that it is a real gas. What if it will not give the A and B? So maglibog ka sa ideal gas and real gas na siya. Then use this Z is equals to PVM RT. To identify lang yun siya if it is a real gas or ideal gas. Okay? Like that. Or the relationship between pressure and temperature. Okay, ganon. So I have also another formula of A and B without referring to the book. Okay, so A is equal to, okay, A is equals to, charot oil. A is equals to the critical volume, oh my gosh, ano namang iba? Critical volume over 3. Nakakaloka. B is equals to 27 B squared times P. Okay, memorize ha? Okay. Muna na siya ang constants ni van der Waals. A is equals to the critical volume over 3. What is, Sir Sotero, what is critical volume? Critical volume will be just equal to the molar volume if the gas will reach the critical point. Okay? Like that. And then you need to know also what's the critical point. And then you ask me like that, it will never end. Okay, research for yourself also in that manner. Okay, so B is equals to 27 B squared times B. B is the constant. Okay, this is, sorry, this is B and this is A. Okay, like that. See, the brain cells are quick to discover, right? So B is equals to BC over 3 and A is equals to 7B squared times B, because there are a lot of redundancies and duplication of the units. So it will, oh, it's wrong. Like that. So it, just like a current, right? Electrons flow in the path or in a wire. When you touch that one, you suddenly like this. Our brain also is like that. If we observe that our representation of our phone are wrong, and then we can immediately change that by quick respond to a specific stimuli. Okay, wow, specific stimuli. Okay, quick response to specific stimuli in biology study, right? Okay, something like that. So, okay na siya. Solve na for this van der Waals, right? Okay. Nakuha na ninyo. Okay, ma-okay din siya. Charot! And in the van der Waals also, we can compute also the Z. There's also Z there. So Z, compressibility factor for the van der Waals or for the real gases is equals to variable coefficient 1 plus the variable coefficient times the pressure. Guys, the variable coefficient will be usually given in the problem. So Z is equals to 1 plus variable coefficient apostrophe times the pressure. Okay? Normally, 1 pressure naman yung i-give ano niya sa mga gases, chupa-chupa sa van der Waals. Unless, ideal. Okay? Ideal, too much pressure siya good to sa P1, P2, P3, ganon. Okay? But here in the non-ideal gas, real gas, is always 1 pressure will be given. Okay? And 1 particular volume will be given. Okay? Something like that. Okay? Yes. You understand now? So these are all about gases, the compressibility factor. Now, guys, before I end this live stream, I have to emphasize also the relationship, the theoretical relationship, because sometimes also in examination, the questions will ask if, for example, if the velocity will go high, what will happen to your temperature? Okay? Ganun siya. Okay? And then, if your molecular weight is less, what will happen to your velocity? Okay? We can answer this through relationship in the equation. Okay? And then through that, we can easily obtain. And if you know the formula, and then you can get the inversely proportional, directly proportional. Basta yung man ay, guys, inversely proportional, if the other one will goes high, the other one will goes lesser or low. But directly proportional, if the other quantity will go high, the other quantity also will go high. There is a direct proportionality, and we can only determine that through the formula. Not necessarily you will memorize. Okay? But if you want to memorize, then go. Because sometimes also you forget the formula, right? So do both. Memorize and understand the relationship. Okay? Something like that. If you want to make sure. Charot. Okay? Ganon. So, ang ating relationship ano niya guys, in this manner is the compressibility factor versus the actual volume of the gas versus the intermolecular forces. Okay. Intermolecular forces can be classified into two. What are the two types of intermolecular forces? Anybody? Okay. Kung nai-solve na ihinay, okay, kung non-negative na ang capacity, the law of magnetism and the law of polarity, okay, it's always a law of opposites. Opposites attract, okay? Opposites attract, right? In the law of magnetism, and same repel. Okay, will never attract with each other. Okay, if you force to attract, then that is LGBT community. Okay, we deviate the standard law of polarity and magnetism. Okay, something like that. And not only for other case. Okay, but here we need to do that. Okay, Z is directly proportional to the intermolecular repulsive forces. By the way, two types of intermolecular forces are repulsive forces and attraction forces. Okay, repulsive meaning will repel. Attraction meaning they will be combined, attached, okay, contact, and they will magnet with each other. Magnetized. My term magnetized. Okay, something like that. Okay, so our compressibility factor is directly proportional to the intermolecular repulsive forces and directly proportional to the actual volume. Now, if I will say that my compressibility factor is less than 1, okay, what is that? You have a very, in terms of intermolecular forces, you have also a less intermolecular repulsive forces. Okay? Because directly proportional, right? I told you a while ago. Okay. If there is a greater Z compressibility factor, then higher your intermolecular repulsive forces, and the actual volume of a gas is high also. Okay. Now, since your intermolecular repulsive forces is very strong or high than the intermolecular attractive forces, now we can say that the gas really in its nature, something like that, is less compressible. Less only. So if it is less compressible, guys, then it is very hard to liquefy a gas. Okay? So you will only liquefy that through certain conditions, but not in a normal way. Okay, because naturally the gas is less compressible magud siya. Okay, if the reverse, it's easy because it's easy to evaporate or vaporize the liquid into gas. But it's difficult, it's very hard to liquefy the natural gas, or the gas ideally from the start. You need to apply some chu. Okay, usually physical and chemical means. Okay, physical means meaning you have to heat that one, you have to change that pressure, like that. And the chemical means you need to add catalyst, something like that. You need to add certain chemicals so that the rate of reaction will be fast, so that the molecules of the gases can easily convert it into a liquid state, because this is liquefaction. Okay, liquefaction is the same as condensation. Don't be confused to that. This is a change from a gas in phase into a liquid phase. Liquefaction and condensation is just the same. Okay? Like that. So you will say it will be condensed, meaning it will turn to liquid. Okay, something like that. The term alone is you should familiarize also, because it will all problems or most of the problems will never say it will turn into liquid at something like this. It will never say like that. Normally it will be condensed into blah 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 chuba chu chu. Okay, so you know already the process of condensation. Then that what it means is liquid or liquefaction. Okay, I'm telling you, so it is a less compressible. Okay, if we have a very high Okay, very, very high. IRF. Ganunin na lang natin, guys. IRF and IAF. Okay, so IMF subdivided into, what do you mean by IMF? Intermolecular forces. IMF classified into two types, the IRF and the IAF. IRF is the intermolecular repulsive force, and the IAF is the intermolecular attraction forces. Okay, and these molecules can be classified into that: attractive, repulsive, attractive, repulsive, attractive, repulsive. Okay, like that. Understand? Now, this is the first proportionality factor. The second will be considered, guys, is the compressibility factor Z is inversely proportional to the compressibility property. So, Sotero, ano ba yung compressibility property? Charot. Okay, compressibility property is composed also of two. If it is less compressible and more compressible. Okay, that's what we mean of compressibility property. Okay, so meaning to say the compressibility factor is not the same when we say less compressible and more compressible. It's the reverse. The, the word factor here. If you don't put the word factor, that would be okay. Compressibility alone. Okay, but if you will put compressibility factor that is inversely proportional to the compressibility or compressibility property that composed of less compressible and more compressible. Now, if we increase the compressibility factor into one, it is less compressible or more compressible? Increase. So less compressible. Okay? Less compressible. So meaning to say, if it is a less compressible, we have also a less intermolecular repulsive forces. Okay. Now, if you decrease the compressibility factor Z, what will happen to your compressibility or compressibility property? It will be more compressible. Okay, so more compressible, meaning to say higher intermolecular attractive forces. Why? Because there are a lot of molecules. Okay, so it will be more compressible. It's easy to compress if there are too much molecules. Okay, if there's no molecules, there's no compression will be done. Okay, the word itself speaks. Okay, more compressible meaning more intermolecular attractive forces. Okay, like that. You understand? Something like that. So we can say now that compressibility property is directly proportional to intermolecular attractive forces. The reverse, right? Okay, for what we stated earlier. So if it is more compressible, then there are more intermolecular attraction forces. If it is less compressible, there is also less intermolecular attractive forces. Like that. Now, my question is, if there is only one mole in an ideal gas, it is compressible or not compressible? That is less compressible. Okay, but still compressible. Okay, so it's still an ideal gas. So that is Z is equals to 1. Right? Because it refers to one mole manggod siya. Okay, one mole of an ideal gas is our reference, right? And then it will occupy 22.414 liter of volume. Okay, under STP. Okay, that's the concept of ideal gas. Okay, so ganun siya. Ganun lang. Okay, again, Z is directly proportional to IRF and thermomolecular repulsive forces and the actual volume. So therefore, we conclude that Z is inversely proportional to the IAF and the actual volume. The reverse. Okay, now, if Z compressibility factor is inversely proportional to the compressibility property, okay, and then compressibility property is directly proportional to the intermolecular attractive forces. Okay, something like that. Because the question usually in the program mentions something like, what will happen if we will increase the compressibility factor? What will happen to the number of moles? A, stays the same. B, reduce. Like this, we increase both A and B. D, none of the above. Since you have no idea for this kind of relationship, you cannot answer. Okay, something like that. Just like Chatillier's principle, right, in chemistry, if you remember that one. From now on, memorize that really because this is very important. Okay, Chatillier's principle discovered in 1818, 1818. Okay, hasta discovery give memorize. Okay, 1818. Okay, whenever a stress is applied to a system of equilibrium will shift in such a way to reduce the stress. And what's concentration, number of moles, and catalyst. Now, the problem in the question in the examination will always they will always give the chemical reaction, and then they will say, if I will add number of moles in the reactant, what will happen? The reaction will shift to the left, will shift to the right, like that. And if you don't have an idea, then you cannot answer. Okay? Something that you should know the relationship with the pressure, the rate of the reaction, the number of moles, like that, like that, like that. And then you will know where your reaction shifted. When you reduce this blah, 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 when you add this blah, 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 when you remove this blah, blah, blah. Also take note also when you add heat, what will happen to your reaction? It will move to the forward, backward, and heat. Again, heat is driven by the change in temperature or temperature ingredients. It's still temperature, right? Because it can never be called a heat without temperature changes and without temperature gradient. Gradient means difference. Gradient means changes. Okay, so that's basically the same thing. Okay, gradient, difference, and changes. Okay, sometimes it will be used interchangeably in the problem solving. We say if the temperature gradient is from like this, from like that, and the difference, and it's up to you. What I mean is master also the terminologies. Master the terminologies because sometimes they will mix up. Okay, mix up in the problem. Usually in our college, it's gonna be like that, and then in the examination, mention another thing. Okay, especially in solubility. Solubility is just an expression of a concentration. Okay, it could be molarity, normality, molality. Okay, something like that. Okay, remember that one. And then you will be confused also because Henry's law. You know Henry's law. The concentration is directly proportional to the partial pressure of the solution. Okay? So maglibog na po ka because the gas is being inserted there. The gas is being inserted in the solution and in the solvent. So all you have to do, oh my gosh, what's happening? So there's a Henry's constant, okay? So studyhin na lang yun ang mga law, mga Waals law, Henry's law, Hess law, Literature principle, Arrhenius Theory, tanan-tanan na gid siya. Clausius-Clapeyron, okay, Carnot cycle, Nernst-Simon postulates, Mr. Gibbs postulate. That's why we have the Gibbs free energy, delta G. Okay, study. The Hess law is more on the discovery of the enthalpy, right? Memorize all kinds of laws in science and the basic formula, and then I assure you, you have a high scores in physical and chemical coverage in the board examination. Okay, sure, 100% sure. Right? Okay, ganun siya. And also the theory of basicity and acidity, that's still Arrhenius, right? Arrhenius theory of acidity and basicity, and we have also Arrhenius theory in the chemical reaction kinetics. You remember chemical reaction kinetics that it describes the relationship between the reaction rate and the temperature. That's still also Arrhenius. That's why we have Arrhenius equation, right? Okay, because basic kinetics are also discussed in chemistry. but not on the more on the calculus part or integral calculus part, because this chemical reaction kinetics involves calculus in solving reaction rates. If you can remember that one, zero order, first order, second. That's why we arrived the ln, the natural logarithm. Okay, because of that integral and differential calculus. Okay, but what I mean, if you are really attentive in your chemistry, the basic foundation of chemical reaction kinetics are already discussed there. Okay, somewhere in the bottom part of the book, of the chemistry book. Okay, chemical reaction kinetics, or shall we say chemical reaction engineering, or shall we say the study how fast and how slow the chemical reaction really is in relation to the activation energy. Wow. Activation energy is an amount of energy that is very necessary to start the chemical reaction. And we preferred a low value of activation energy from the start. Okay, because if you have a low value, then it will just proceed the chemical reaction. There's no problem anymore. We don't have to apply heat. We don't have to apply more temperature. We don't have to apply more pressure. We don't have to apply more catalyst. We don't have to apply more inhibitor to slow down the reaction. Okay, we don't have to apply any chupa-chucho. Okay, or we don't have to put that in a certain container with a higher diameter so that it will just react fast. Okay, because reactions also matters in the container. If the container also is very congested, the molecules will not also move freely, congested, obstructed. Then that's the time you heat more, right? So that it will just be, interacted with each other, so that the intermolecular attraction forces will be increasing, especially when the container is closed. Oh my gosh, it cannot escape into the atmosphere. Charot. So you need more heat for that. Something like that. Okay? So that's very clear. Charot. So these are really interrelated. So sa totoo naman, chemistry ang gamhanan sa tanan. Because in physical chemistry, Chem, there's a lot of chemistry there. Okay? And then in thermodynamics, there's a lot of chemistry there also. And then in physics also, there's a lot of topics of chemistry there. Because internal energy, enthalpy, blah, 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 so on, so are discussed also in physics. Okay? Like that. And thermodynamics, like that. And unit processes also have chemistry. Okay. That's why pala, you can never take those subjects without passing the chemistry 1 and 2. Okay, like that. Okay, something. And some of it, guys, can be solved only by algebra and trigonometry. No need to worry of integral and differential calculus. If you reach in the physical chemistry on the topic of work, blah, blah, chuba, chucho, right? There's a lot of equation in the isothermal thermodynamic process. The formulas are, wait, I have to recall. Okay. W is equals to nRT/ln, initial pressure over the final pressure, or it could be nRT/ln, final volume over the initial volume. Okay, there's an ln there. Why? Because it involves integral and differential somewhere along in deriving that particular equation. Okay, so since it's already there, it's already derived. You don't go back to derive, so you use now algebra. Malong, you use now algebra. All you have to do is to substitute numbers na lang. Okay? Because the derivation is in the first part. That's why we obtain an ln. Okay, in the equation. So basically, algebra na siya yun. Okay, to substitute, to analyze, like this. So majority of the computation can be used by algebra alone. Okay, those other things are only another method to produce the same answers with algebra. Something like that. If you can remember your integral, right? Computation of the volume of the area, try to solve it by algebra. You'll get the same answer. Even though you use the integral calculus method, differential calculus method, and then you find out what is the volume of a sphere. Ganon, and then solve that also in algebra without integration and without differentiating it, you will obtain the same answer. Okay, because that's only another method or alternative method to get the correct answer. Because in real world, you don't have to deal with calculus just to obtain simple mathematics or whatever chupa chuchu in your job. Okay, like this. You only have algebra and trigonometry and kalas, something and a little bit of science, concepts in science, the basic concepts of science, of course. Okay, something like that. Okay, and you don't have to worry. Okay, you will worry that only in your general engineering coverage because integral calculus and differential calculus, differential equation, and advanced engineering mathematics will be coming out there in the exams. Okay, what I mean in the major, chupa in the physical and chemical, you don't have to worry about integral calculus and mga chupa-chucho in anak. We can solve that algebra. Okay. The only difference is very lengthy. Lengthy. You have to cut this one. 1, 2, 3, 4, 5, 6, 7. For example, heat exchanger 1. Calculate the heat transfer there. Heat exchanger 2. Or calculate the heat transfer. And the value of that 2 will be obtained there. And you can go to the heat exchanger 3. If you will not solve the heat exchanger 1, heat exchanger 2, heat transfer. Like that. The same also with distillation. There's a lot of distillation columns, distillation column 1, distillation column 2, distillation column 3, and you will get the distillates and the condensates in each distillation column. You can never go to 2 and 3 if you will never solve 1. Okay, so though you are trying to put that equilibrium stage or steady state flow so that you can get easily the answer, law of conservation of energy, right? So, uh, 1. Distillation column 1 is equals to distillation column 2 and equate that there so that you can solve the answer and you can use that also in distillation column 3. Because without equilibrium stages, guys, you cannot solve the answer. That's the purpose there. That's why we have equilibrium stage in science to make our life easy. Okay? First example, the most basic example is the heat regulation in our body. Our body core temperature is 37 to 38 degrees Celsius. Now, if the environment outside is very hot, high humidity, we have a natural regulation of our temperature in our body. So we need cooling system so that there will be an equilibrium between the temperature outside the environment and the temperature inside our body. So that's why equilibrium principle is very important, not only in the chemical reaction, but also for human being. Without equilibrium stage, then we will die because our temperature will not regulate. What will happen if you are too much hot? So you have high fever, right? And then if you will not go to the hospital, what will happen? So something wrong with yourself now already. So there must be a regulation of the heat outside and inside your body, and it must be in equilibrium. Okay, that's why we need cooling, heating and cooling must be in equilibrium to survive in this planet Earth. Okay, so that's still under the thermodynamics. Okay, in science. Okay, really. So science is the most powerful subject all over the world. Without it, we will die. Okay, without money, we can survive. I tell you frankly, even though without money, we can survive because we want to eat. If you are just very hardworking to plant in your garden, then you can get food in your garden, even though you will not buy food in the market, right? And you will survive. You will drink water. You will drink the fruit in your garden there in the mountain. Okay, so that's science, right? And then even though you don't have money, you will survive. Okay, and that's important. Okay, so thank you so much for watching this live stream. I hope you understood a little bit about this compressibility factor to distinguish between a real gas from an ideal gas, and you can compute such those quantities. A lot of equations will be used also. Okay, here. Okay, then bingo, you can solve what is being required talaga siya. Okay, thank you so much. You can comment down below in the comment section. You can subscribe to my YT channel if you want also. And you can also click the notification bell for subjects at this MSc National Voice, Safety Engineer, and a licensed chemical engineer from Cebu Institute of Technology University. Bye bye. God bless everybody. Thanks so much for listening. See you later.